So I'm going to quickly recap what we did last time. We said that electrons, they occupy orbitals, and electrons, they exist as, you can think of them as bees swarming around sweets. So, Sanjita, can you hear me now? I said so. So electrons, think of electrons as bees that are occupying, that are attracted to the nucleus and that are occupying a certain region. So s orbital was spherical shaped. It would be a spherical shaped region. A p orbital would be a double shaped region, and it's directional, which means that there are three different types of p orbitals depending on where the electron exists. It could be lying on the x-axis, it could be lying on the y-axis, it could be lying on the z-axis. So there are three different types of p orbitals: px, py, and pz. They're all identical. They have exactly the same energy level, and they're called degenerate orbitals because they're identical. They exactly have the same shape. The only difference is that the directions are different, and together it's called a p subshell. Px, py, this entire thing is called a, it's called a p subshell. It's a group. A subshell is a group of degenerate orbitals. The s subshell has just one s orbital because it's not directional. You rotate an s orbital, you get the same thing. Then you had the d orbitals. D orbitals have the electron in a d orbital would exist in four lobes around the nucleus, and that's also directional. The lobes could exist between the z and y axis. They could exist between the electron could exist between the z and x axis. It could exist between the x and y axis, or it could exist. The electron could lie on the x and y axis, or it could be on the z axis. So there are five different areas. There are five different directions of the d orbital. The last orbital is kind of slightly different looking, uh, but together this is called a d subshell. D subshell has five orbitals. There are five different arrangements of a d orbital, and there are five different types of degenerate d orbitals. So the next thing that we studied was subshells. I told you that each orbital can have a maximum of two electrons. So all these regions in space around the nucleus, they all can have a maximum of two electrons. So you have an s subshell. It only has one s orbital, so the maximum number of electrons are two. There's a p subshell. It has three orbitals, px, py, pz, and the maximum number of electrons that can be accommodated in a p subshell is six. I mean, this is a p subshell. Two electrons could occupy this orbital. Two electrons could occupy this orbital. And similarly, two electrons could occupy this particular orbital. And then there's an F subshell as well, which has seven different F orbitals. Usually, no one discusses F subshells because most atoms don't have an F subshell. Very, very large atoms, they have F subshells. So we're not going to discuss or go into their detail, but you just need to know that an F subshell has a maximum of seven orbitals, and each orbital has two electrons, so there would be a maximum of 14 electrons. And similarly, the D has five D orbitals. Each can accommodate a maximum of two electrons, so there could be 10 electrons in a D subshell. So we talked about subshells. So regions in space around the nucleus where there's a high probability of finding an electron. And then we talked about shells. The idea of a shell, uh, unlike O levels, in O levels, a shell was this spherical ring around the nucleus. But over here, shell is known as a principal quantum number, and it denotes the energy level of an electron. And what it simply means is that each subshell is going to have a shell number written next to it. If it's one, that means the electron is not very energetic. If it's two, that means the electron has more energy. If it's three, so shell numbers, they represent the energy level of the electron. And the only difference that would make is that if the electron is energetic, then it's going to, if it's not very energetic, then it would occupy regions very, very close to the nucleus because it won't be able to, the electron, think of it as a fly that's hovering around the nucleus, attracted to the nucleus. And so if this electron is not very energetic, then it would just stay very close to the nucleus. If it's more energetic, then it would go much further away from the nucleus. Or if it's in the third shell, then it would be very energetic and the electron would occupy regions much, much further away from the nucleus. So The difference a shell would make is that it would represent energy levels, and at higher energy level, the electron would be much further away from the nucleus. It would occupy areas that would be much further away from the nucleus. So we've still not learned how to actually fill electrons in an atom. What we have discussed is that there are orbitals which can be grouped into subshells, and each subshell will have a particular energy level that would be denoted by its shell number. The next tiny bit that we're going to do is we're going to learn how two electrons occupy a single orbital. Okay, so we are still not learning how to actually write electronic configurations just yet. So the next thing we're going to learn a tiny bit, that's how two electrons occupy a single orbital. This is what we discussed earlier, that each orbital can have a maximum of 2 electrons. So here's your nucleus and here's an s orbital. And the maximum number of electrons an orbital can accommodate is 2. Now, electrons inherently repel each other. So two electrons should not so two electrons, technically they should not be occupying the same region because they're going to repel each other. Both electrons are negatively charged, and since both of them are negatively charged, they are going to repel each other. So ideally, like if you look at the p orbital, if you look at this p orbital, let's talk about the pz, this blue orbital over here. It shouldn't have 2 electrons in it. I mean, this region in space around the nucleus should have 1 electron, because if the second electron is going to repel the first electron. So how can 2 electrons occupy a single orbital? Because they're going to repel each other. So how do they do that? The way they do that is that every elementary particle has a magnetic field associated with it. And this is what happens, that the magnetic fields of the 2 electrons, they attract each other, which cancels out the force of repulsion. Every elementary particles, whether it's a neutron, proton, or electron, they all have, not only do they have a charge, they have 3 things. They have a mass, they have a charge, which is for an electron, it's negative, and every single elementary particle, for example, even an electron, is going to have a north pole and a south pole. It's going to have a magnetic field. So what's going to happen is that both electrons and the magnetic fields are known as magnetic dipoles. So both electrons have opposite spins. This is another word that's used for the magnetic field. Spins is a magnetic dipole. A dipole simply means north pole and south pole. And the correct word is, it's called a magnetic dipole moment. So what it simply means, it's in simple words, that 2 electrons, they can only occupy the same orbital if, I mean, the electric fields are always going to repel each other, but they're both negatively charged, so they're going to repel each other. But the magnetic fields, which I've shown in green over here, they should be attracting each other. So for example, if you have a north pole over here, the other one, I mean, ignore the arrows for a second, the other one should have a south pole. So they should have opposite magnetic dipoles so that they can attract each other. Because if both electrons have north poles on this side, then the problem would be that even the magnetic field would be repelling. So the 2 electrons can in no way then stay in the same orbital, because there's going to be too much repulsion. The negative charges would be repelling each other, and the magnetic fields would also be repelling each other. So you want the electrons and the magnetic fields to be opposite, so that they start to attract each other. So this is how two electrons can cancel out their force of repulsion. Both electrons are negatively charged, they repel each other, but both electrons have opposite spins or opposite magnetic fields. So they attract each other, which cancels out the force of repulsion. Cancels out the electrical force of repulsion or electrostatic force of repulsion. Okay, so remember this thing always, that electrons in an orbital, they always have opposite spins. Is the idea clear? Yes or no? Is this clear? Rida, Sanjida, Minahil. Okay. So remember, both electrons, their magnetic field should be opposite to each other. Only then can they start attracting each other and they can stay in the same orbital over here. So the way this is represented is, okay, we're going to do this later on as well. Usually an S orbital or any orbital, there would be a representation that we're going to study later. And in that representation, both electrons are represented by arrows. One would be pointing upwards, the other one would be pointing downwards. So this is one way of representing these opposite spins. So if there's an orbital, the orbital would be represented by a box, and each electron would be represented by an arrow. Make it a full arrow. One of the electron must be pointing upwards, the other electron must be pointing downwards. That shows that they have opposite magnetic fields or magnetic dipole moments, or you can call them spins. Now, another tiny bit is, how is a subshell filled? Okay, so before we actually learn how to write electronic configurations, we must know how to fill a subshell first. So a subshell was a group of degenerate orbitals or the same type of orbitals like px, py, and pz. Together they were known as the p subshell. Okay, this was known as a p subshell. I said, let me quickly draw a p subshell. It's going to have so this is 3-axis, and there's going to be a px orbital. An electron could exist in the px, it could exist in the py, or it could exist in the pz orbital. So that's a p subshell. So if you're trying to fill, let's say, the maximum number of electrons that could occupy this p subshell, that's 6 electrons. But how would the electrons be filled? So an electron is always filled. I mean, a subshell is always filled in a single manner first. What that means is that if you, let's call this the px orbital, if you fill an electron in a px orbital, 1 electron, then the next electron would not actually go into the px because there's going to be repulsion. There's already an electron there. Whereas the other orbitals are empty, completely empty. They're empty spaces. So if you are trying to fill the second electron would actually occupy the empty orbital because that's more convenient for it. And then if you're trying to fill the third electron would not go in these orbitals, the shaded ones, because there's already an electron there. It's going to fill the empty space over here. So it's going to fill the pz orbital. So the rule is electrons in a subshell are always filled in a single manner first. So they're always filled in a single manner first. And then once they have been filled in a single manner, and then are doubly filled. Which means that once one electron has you've added one electron each in each of the orbitals, and electrons are always written on top, okay, like an exponent, they're written on top of the orbitals. So once one electron goes into each of the orbitals, then the fourth electron would then start filling, and the orbitals would become doubly filled. Then the fifth electron would occupy this particular orbital, and then the sixth electron would occupy this particular orbital. So if somebody is asking you to describe what the p subshell would look like if there are two electrons in it, with two electrons, so you're going to show them that it's going to have the p subshell is going to have three orbitals. And if there are two electrons, then the first electron would go and occupy the px, the second electron would go and occupy the py, and the pz would be completely empty. Similarly, if somebody is asking you to show them how three electrons would occupy the p subshell, then that means the px, py, and pz, one electron would go in the px, the other one would go into py, and the third one would go into pz. And similarly, if there are four electrons, then that means that one electron each would be filled in all of the orbitals, and then the second electron would go in the px. So remember how subshells are going to be filled. In any subshell, that includes the D subshell as well. I mean, the D subshell, I mean, if you look over here, the D subshell can have a maximum of 10 electrons, but if you're filling 5 electrons, then, or if you're filling 3 electrons or 4 electrons in a D subshell, then first they should all be filled in a single manner first. One electron over here, one electron goes over here, one over here, one over here, then one over here. And after that, once they're all singly filled, then you start pairing them. You start adding the second electron. Okay? Is this point clear? Yes or no? Is this clear?
Yes.
Achha, so we've learned everything about orbitals, subshells, shells, and we've learned about how to fill electrons in an orbital, that they should be having opposite spins, and we've learned how to fill a subshell, that it's always going to be filled in a single manner first. Now the thing is, we're going to learn how to write electronic configurations. Okay, so you have so many subshells, you have so many orbitals, you have so many shells. How do you write an electronic configuration? How do you figure out whether an electron is an s or in a p or in a d orbital, and which energy level, etc.? So the Aufbau principle, it provides us with, it tells us how to actually fill or write electronic configuration. This table is simple. So it's 1s, 2s, 3s. I mean, this big 3 represents the energy level. 4s, 5s, and let's write 6s. And right next to it, it would be 2p. There's not going to be any 1p. So 4p, 4d, sorry, this would be 5p. And then you're going to have the d orbital, which starts from the third shell. So it's going to be 3d, 4d. etc. And you're going to have, if there is a requirement, which usually there isn't, you'll have the 4f and the 5f and etc. So the table just continues. So why does the first shell? The first thing, why does the first shell have just one? I mean, the numbers are the shell numbers. They are the energy levels. Why does the first shell have only one orbital? The reason is that the first shell, the energy level is so low that the region that the electrons would be occupying, you can't fit a lot of electrons around it. Okay, so, and as the energy levels increase, the electron occupies regions much further away from the nucleus. So you have bigger regions and more electrons can actually fit into those bigger areas. So the first shell does not have a lot of orbitals because you can't accommodate, it's a small region, you can't accommodate a lot of electrons in the first shell. So how do you figure out the order in which these subshells are going to be filled? Okay, remember these are subshells. So you're going to draw these diagonal arrows and you're going to fill these diagonal arrows starting from top to bottom. And every time it's going to be exactly the same. So for example, you have sodium and sodium has 11 electrons in it. So that means you're going to start off with the first one, which is 1s. The 1s is going to have a maximum of 2 electrons. The 1s subshell only has 1s orbital. After that, you follow the arrows, the second arrow. So this is 2s. So that's going to have a maximum of 2 electrons as well. So it's an s orbital in the second shell. Then you have the 3s. And one mistake that I've made is I've drawn the arrows. I mean, the arrows are pointing in the wrong direction. Just one second. That's one mistake. Let me correct that. I mean, the arrows are pointing downwards. You have to travel downwards. Okay, now I've corrected that mistake. So we can ignore this side. Okay, so it's going to be 1s, 2s. Then it's not going to be 3s. It's actually follow the arrow. It's going to be 2p and then 3s. So the 2p subshell would have a maximum of 6 electrons, and then that's a total of 10. Then you're going to have the 3s, which is going to have a maximum of 1 electron. I said, Rida, I'm going to talk about that just in a moment. Okay, I'm going to talk about that. So this is how you're going to write the electronic configuration, and pretty much for any atom, the same electronic configuration or the order of filling subshells and would be followed. So what would sodium look like in reality? If I try to sketch sodium, like sodium is going to have a nucleus. There's going to be 2 electrons in the 1s orbital. The 1s orbital is going to be a tiny region around the nucleus where there would be 2 electrons. Then there's going to be 2 electrons in the 2s orbital. The 2s is going to be slightly more energetic, and it's also going to be a spherical region. So it's going to be a much bigger area. And there are going to be 2 electrons which are more energetic. I mean, the first 2 electrons are occupying this area. The next 2 electrons are occupying a much bigger area. Remember, these regions, they overlap. I mean, the 2 electrons over here, they would be occupying a much bigger area. The first 2 electrons would be occupying a much smaller area. These regions are all overlapping. Then you have the 2p. I mean, it's like flies buzzing around sweet substance. The flies are all, I mean, they're occupying the same area, overlapping areas. But I mean, you treat them as different areas because the electron over here would have a different energy. I mean, it's going to occupy this region, but it would be more energetic. So the orbitals or the regions and spaces, they would be overlapping, but the electrons would still be treated as separate because they have different energy levels. Then you have the 2p6. Now the 2p6 means that there's going to be an x-axis, a y-axis, and there's going to be a z-axis. And they're going to be electrons 2p6 So there's going to be 2 electrons occupying this area over here. There would be 2 electrons occupying this area over here. And there would be 2 electrons occupying this area over here. And finally, there's a 3s. 3s means that there's going to be a spherical region, but it's from the third energy level, third shell. So the electron would be very energetic, and that particular electron would be occupying a much, much bigger area because it would be the most energetic electron. So that would be your 3s. So every time you remove an electron, like if you remove the 3s electron, then the electron over here, this particular region, the negative charge over here would disappear. So right now I'm going to bring that in. So this last electron would be occupying this much bigger area. So all the electrons are kind of overlapping with each other, but every time you remove an electron, a negative charge would disappear from a particular space around the nucleus. So the electrons are all overlapping, but they're all unique and distinct at the same time. Okay, it's like flies buzzing around a sweet substance. They might be occupying the same region, but they are all distinct. Acha, so this is what sodium would look like. And every time you're going to write the same, pretty much the same electronic configuration. So I'm going to do iron for a second, 26 electrons. Okay, I'm going to talk about what Rida just said. So 26 electrons. 26 electrons, if you follow the electronic configuration, it's going to be 1s, 2. Then it's going to be 2s, 2. Then it's going to be 2p6. Then it's going to be, after 2p6, it's going to be 3s2. And then after 3s, it's going to be 3p6. Then you're going to have 4s2. Okay, now look what I'm doing over here. Okay, I'm writing 4s. I mean, 4s is going to be filled. And then I'll have 6. I mean, this is 20 electrons. Then I'll have 6 electrons left. So 3d would come later. So now what I did over here was, I mean, let me put this like this first. So this was the order of filling of electrons according to the table that we just drew. Okay, this is the order of the filling of electrons according to the table that we just drew. Remember, this table is just a shortcut for us to figure out the electronic configuration. Remember this is the first shell. Okay, now listen just for a second. This is the first shell, shell number 1. It's the lowest energy shell. It's always going to be filled first. Then 2s and 2p6, these are your shell number 2, slightly higher energy level. So they're going to be filled after that. Then you have the third shell. Remember the third shell, and let me put the fourth shell slightly outside because the fourth shell is further away. The third shell should be filled. It should always be filled before the fourth shell. So right at the end, the fourth shell or the outermost shell or the most energetic electron, which would be much further away from the nucleus, that region would be filled. So this is shell number 3 and this is shell number 4. But according to the Aufbau principle, this is not what's happening. Like if you 2p is filled, then 3s is filled, then 3p is filled, then 4s is filled before the 3d, the 4s orbital, and this is what we did as well. Like we were filling electrons, we did not fill the 3d first, we filled the 4s and then we filled the 3d with 6 electrons, and that gave us a total of 26 electrons. So the issue is, why is the why is the 4s getting filled before the 3D? So the simple answer to this is that in reality you're not actually filling electrons. No one is filling electrons. Okay? An atom already, I mean sodium, if you look at a sodium atom, no one is picking a sodium nucleus and starts filling electrons around it. Okay? So in reality, no one is actually filling electrons in an atom. The electrons are always there from the start, from the beginning. Like sodium has 10 or 11 electrons, TK, depending if it's forming an ion. So the electrons are always there. So no one is actually going there filling electrons, TK. No one is going there, okay, let's pick 1s and put 2 electrons over there, then pick 2s and then put 2 electrons, then 2p and put 6 electrons over there. So, no, so in reality, none of these atoms, uh, no one is actually filling electrons in these atoms. So the order in which the electrons you're filling, that's irrelevant because in reality, no one is actually filling electrons. The electrons are already there. Okay, they're always there. Okay, from the beginning of the universe, the electrons are already filled in an atom. Okay, so the thing is, what this table gives us is just the electronic configuration. So you just follow the electronic configuration. The table doesn't matter whether 3D gets filled after 4s because in reality, you're not actually filling electrons. What you just need is this electronic configuration. So you get this electronic configuration, and the electronic configuration tells you that the 4s is the outermost orbital, and it has 2 electrons, and the 3D has 6 electrons, and so you get the electronic configuration. And atoms' electrons are always present from the beginning of the universe; they're always there. Okay, so you're not filling electrons in the first place, so it doesn't really matter. This table only gives us the way to write this electronic configuration or figure out the electronic configuration. So at the end of the day, it's completely irrelevant whether while you're doing this, whether you fill 4s first or not. Okay? So the whole idea of filling electrons is completely irrelevant. Reza, do you get the point? ठीक है, बाज गए? ठीक है. So just remember this table and the order in which the electrons are filled. This table is only used to give you the electronic configuration of the atom. Okay? And correct this table. Once you're done filling the electron, the 4s must always be on the outside because it's the higher energy orbital. Although the 4s is filled first before the 3D, but you're going to write the third shell orbitals first, followed by the 4s orbital. Okay? And when you're filling it, although according to the table, the 4s is going to be filled first. So write 2 over here and keep some space for the 3D because the third shell is going to be before the 4s. So the 6 electrons would go over there. So the table is only used to give you an idea of the electronic configuration. Okay? No one is filling electrons in the first place. So the order of filling electrons in these orbitals, it's only there so that you get the right electronic configuration. Okay? And that's going to be the electronic configuration of iron. And I'll also explain why the outer shell actually gets filled before the 3D subshell. The reason that happens is that the third shell has so many electrons, like 2 electrons, 6 electrons, and another 6 electrons, that there's a lot of repulsion in the third shell. There are too many electrons in the third shell. Think of this as the region of the third shell. So D can have a maximum of 10 electrons. But when you reach 6 electrons, there's so much repulsion, there's so many electrons in the third shell that for any further electrons, it becomes easier to actually move further away from the nucleus and occupy the fourth shell, slightly further away because of the repulsion. So this is what happens. So the shells, the rule is that the inner shells don't need to be actually completely filled for the outer shells to start filling up. So we can do another example. Okay, let's quickly do scandium. Scandium has 21 electrons. So according to the table, the Aufbau principle, it's going to be 1s2, then 2s2, then 2p6. Okay, then it's going to be 3s2, then 3p6, and after 3p6, where were we? 3s2, then 3p6, then 4s is going to be filled. So keep room for the third shell. So 4s would be filled. Now you have 20 electrons, so there's 1 electron left. So after 4s, what do you get? You get this 3d. So 3d would have just 1 electron. So that's how you write the electronic configuration. Make sure you group the shells together. The second shell's orbitals must be grouped together. The third shell orbitals must be grouped together. Just to show you that the outermost shell is still the 4s. Okay? And it doesn't matter in this table in what order the electrons are getting filled, because the electrons, no one is filling electrons. The electrons are already filled from the beginning. So is this clear? The Aufbau principle. Okay? I'm going to give you a small assignment. Try and write the electronic configurations of all these atoms and send the answers on WhatsApp. It's barium, then bromine, sulfur, lithium, and let's say silver. So that's your assignment. Try and write the electronic configuration based on the Aufbau principle. I'm going to send this on WhatsApp as well. So is this clear, Bazga, Minahil, Rida, Sanjita? Is this all clear?
Yes.
Okay, make sure you send the answers on WhatsApp, okay, of these elements. So we're going to continue with this, TK, in the next class then. And I'll send you I think I've sent you the ideal gas worksheet. Try and go through the ideal gas worksheet. Okay, then if you don't have any questions, take care. Allah Hafiz.